Scientists were able to make a breakthrough over the presence of a black hole in the universe thanks to the simple calculations from a legendary German scientist to crack Einstein's unsolvable theory. Albert Einstein's general theory of relativity is the genius equation that helped explain how gravity is a universal product of space and time or spacetime. Tabled in 1915, the German scientist detailed that the curvature of space is directly related to the energy and momentum of whatever matter and radiation are present within. However, there was a problem. Einstein could not explain exactly how to prove his theory as he could not produce the correct calculations and so used approximation instead when presenting his paper. That all changed a year later when a soldier in World War II called Schwarzschild proposed the Schwarzschild solution in a letter to Einstein. Oxford graduate Simon Clarke explained exactly what happened on his YouTube channel. He said last year, Einstein's theory solves the problem of what causes gravity. It's the curvature of space-time. He had a problem though. The equations describing this were too difficult for anyone to solve, even Einstein. Einstein thought the equation was too complicated to get an exact answer for, but somebody fighting though different called Schwarzschild. During the war he kept up to date with the latest research and heard about Einstein's work on gravity. So while serving on the Eastern Front in what is now Lithuania, he got to grips with the equations of Einstein's theories. Mr. Clarke explained how Schwarzschild solved the mystery. He added, Schwarzschild thought there was a way to solve Einstein's equations exactly what Einstein had missed. So when a lull in the fighting presented itself, he did so with the simplest case possible. A non-electrically charged, non-rotating, homogeneous and perfectly spherical mass. It's basically a ball of mass. Schwarzschild was able to derive a geometry which satisfied Einstein's equations, and so described the four-dimensional spacetime, or the grid, surrounding a non-rotating blob of mass. Mr. Clarke added, he wrote to Einstein with his work and received a very impressive letter in response. The letter to Einstein was as follows. I have read your paper with the utmost interest. I had not expected that one could formulate the exact solution to the problem in such a simple way. I liked very much your mathematical treatment of the subject. However, in solving Einstein's theory, Schwarzschild had identified another phenomenon in space, what would later be known as a black hole. Mr. Clarke continued, Schwarzschild's result was correct and brilliant, but there was something strange in it. Specifically the term where r is the distance from the center of mass that you are considering. When r equals r, s, this term becomes infinite, which produces some unusual behavior. In this distance from the center of any mass, now called the Schwarzschild radius, space-time is so curved that not even light can escape from within. The Schwarzschild radius defines the size of the black hole in space-time and forms the boundary objects which get caught in the influence of a black hole fall towards. If you watch an object falling into a black hole from far, you'll see it fall slower and slower towards the Schwarzschild radius, but never actually reach. Schwarzschild defined the key characteristics of a black hole, something that Einstein hadn't done. It took his theory and Schwarzschild's work on it before we arrived at our modern understanding.